I want you to picture something really mundane for a second. Picture the back of your Wi-Fi router.
Okay.
There's probably a little black cable screwed into it or maybe into the wall. It's plastic, got a bit of copper inside. It looks like the most boring object on planet Earth.
It is deceptive, isn't it? Because that little cable is doing some heavy lifting.
Exactly. You
Yeah.
tend to think of it as just a pipe. You put the internet in one end, it comes out the other. But looking at the research today, if you were small enough to actually stand inside that wire while the signal was moving, the rules of reality would look completely different.
That is not an exaggeration. You'd effectively be standing in a non-Euclidean universe.
And that is exactly where we are going today. Welcome back to the Deep Dive. We are unpacking a stack of research that bridges high-level theoretical math and, the gritty reality of engineering. We're talking about the hidden geometry of radio frequency, or RF, engineering.
It's a fascinating topic because it's currently undergoing this massive generational shift. We're moving from how humans visualize these invisible signals, which we've done for 100 years, to how artificial intelligence perceives them.
The sources describe this as a transition from the human era of tuning to the machine era.
That's the mission for this deep dive. We need to understand how we got from the Smith chart, which is this beautiful, iconic visual tool engineers have used since the 1930s, to a new mathematical framework called rational trigonometry.
Rational trigonometry,
Yeah.
which implies that normal trigonometry is irrational.
In a mathematical sense, yeah, it often is. But the rational here refers to a specific algebraic framework designed for autonomous robots.
And just so you understand the stakes here, we aren't just geeking out over math for the sake of it. There's a reason this shift is happening now.
Absolutely. This is critical infrastructure. This transition is the difference between an engineer manually tuning a radio dial and the high-speed, no human-in-the-loop automation that makes 5G and 6G possible.
Yep.
If you want your phone to maintain a connection with a satellite while you're moving, or a cell tower to beamform a signal instantly to a million users, you can't use the old geometry.
Okay, so to understand the new stuff, we have to understand the old stuff, and that starts with the physics of the wire itself. I think most of us have this mental model of electricity acting like water in a pipe.
Mm-hmm.
You turn on the tap, the pressure pushes the water down the tube in a straight line. Why doesn't that hold up here?
That water analogy is perfect for DC or direct current, like a flashlight battery. It flows one way.
Yeah.
But in RF, we're dealing with alternating current moving at incredible frequencies.
Millions or billions of cycles per second.
Exactly. And at those speeds, the physics changes.
Completely.
The wire stops acting like a simple pipe. It becomes a transmission line. To describe it, physicists use the telegrapher's equations. Imagine shouting into a long, tiled tunnel. The sound doesn't just travel away from you. It bounces off the walls. It reflects back at you. It gets quieter, which we call attenuation. And the timing, or phase, shifts. The signal is constantly interacting with the medium.
So it's not a straight shot. It's a chaotic environment of reflections and echoes.
It is. And here's where the geometry breaks. If you try to map that movement using standard trigonometry, the circles and triangles you learned in high school, it gets incredibly messy.
So the map that actually describes this movement doesn't use standard sine and cosine.
No, it doesn't.
What does it use?
It uses hyperbolic functions. You might have seen sin and cosh buttons on a scientific calculator and wondered what they were for. That's hyperbolic sine and hyperbolic cosine.
Okay, so hyperbolic. I know that word usually means exaggerating, but in geometry it refers to the shape of the space, right?
Exactly. Think about the surface of a sphere, like a basketball. That has positive curvature. If you draw a triangle on it, the angles add up to more than 180 degrees. It sort of bulges out. Now imagine the opposite. A surface with constant negative curvature, like a Pringles chip or a horse saddle.
A saddle shape.
That is a hyperbolic space. And mathematically, a transmission line behaves exactly like that saddle-shaped surface.
So the signal isn't traveling through a flat tube. It's traversing a saddle-shaped mathematical universe.
Precisely. And this creates a huge problem for engineers. Humans are terrible at visualizing negative curvature. We can't just look at a saddle shape and intuitively know where the voltage is or how to tune the antenna. We need a map.
And looking at the research, this is where a piece of math magic called the Mobius transformation comes in.
This is the engine of the entire field. In RF engineering, you have two distinct realities. First, you have the world of impedance.
Okay.
That's the physical resistance and reactance in the wire. That world is infinite. We call it the right half plane.
Because resistance can go on forever. You can have infinite resistance.
Exactly. But you can't graph infinity on a piece of paper. It's useless for a technician who needs to calibrate a transmitter. So the Mobius transformation is a function that takes that infinite right half plane and it warps it. It squashes the entire infinite landscape onto a finite circle.
It's called the unit disk.
The unit disk. It captures infinity inside a circle.
That's wild.
Yeah, it's similar to how we map the spherical Earth onto a flat paper map, but much more aggressive. It maps an infinite energy landscape onto a small, manageable circle, and that circle became the basis for one of the most famous diagrams in engineering history.
The Smith chart.
The Smith chart.
I've seen these. Even if you aren't an engineer, you might have seen them on T-shirts or in old physics labs. It looks like a grid of circles that has been warped and twisted. It's complicated, but it has a certain, I don't know, aesthetic to it.
It is iconic. It was invented by Philip Hagar Smith in the 1930s, and for decades, people just treated it as a really useful chart. But here's the insight that usually floors people. The Smith chart isn't just a chart. It is the Poincaré disk model.
The Poincaré disk model. That's a heavy math concept. That connects to art too, right?
Yes. You know those M.C. Escher prints, specifically Circle Limit 3, where you have angels and devils interlocking?
Oh, yeah.
And as they get closer to the edge of the circle, they get infinitely smaller.
Right. They never actually touch the edge because the space is getting compressed.
That is the Poincaré disk. It's a model of hyperbolic geometry, and the Smith chart is the exact same thing.
So, wait. For 80 years, electrical engineers have been using high-level non-Euclidean geometry to tune radios.
Often without even realizing they were doing advanced math.
They were just following the lines on the chart.
Exactly. It works because of how the lines behave. In this geometry, a straight line, or a geodesic, isn't straight on the paper. It appears as an arc.
So if I'm an engineer in 1950, and I'm tracing a line on this chart, I'm actually tracing the shortest path through hyperbolic space.
You are. If you have a perfect lossless transmission line, you trace a perfect circle centered at the origin. You're just rotating around the center of the hyperbolic world.
But real wires have resistance. They lose energy. The notes call this lossy.
Right. If the line is lossy, you don't get a circle. You get what's called a loxodromic path.
Loxodromic. Break that down for us.
It basically just means a spiral. As the signal loses energy to heat or resistance, it spirals inward, shrinking toward the center of the chart.
It's incredibly elegant because it turns complex calculus into a drawing exercise.
It was an analog computer. That's the best way to think of it. Before we had digital calculators, an engineer could take a ruler and a compass, draw these arcs, and physically measure the rotation. They were calculating hyperbolic rotations by drawing on paper. That was the art of tuning.
And that art form dominated for decades. I mean, it got us to the moon, it built the radio network.
Yeah.
But the sources indicate we hit a wall.
We did.
A no human in the loop wall.
The world changed.
But I have to ask, if the Smith chart is so intuitive and it models the physics perfectly, why are we trying to replace it?
Because intuition is for humans. Robots don't have intuition, they have processors. And it turns out the math that generates the Smith chart is, well, it's a nightmare for computers.
Why? Computers are supposed to be good at math.
They are good at discrete math, logic, arithmetic. But the Smith chart relies on transcendental functions: sine, cosine, tangent, the number pi, the number e.
And those are hard for a chip.
They're surprisingly heavy. A computer chip doesn't natively know what sine of 45 degrees is. It has to run an approximation algorithm, usually an infinite series, to guess the number.
So it's essentially doing a lot of calculations to get an answer that is slightly wrong.
Exactly, it's an approximation. And in complex simulations, those tiny rounding errors accumulate. It's called numerical drift.
I see.
If you're simulating a massive 6G network with thousands of nodes, by the time you get to the end of the calculation, your answer might be significantly off because of those tiny errors stacking up.
And I assume speed is a factor too?
Huge. To calculate these complex exponentials, the processor needs a floating point unit, or FPU. That is a complex physical part of the silicon chip designed to handle decimals and exponents. It is power hungry.
Right.
If you are a satellite in orbit running on solar panels or a remote 5G tower, you don't want to waste your energy budget crunching sines and cosines.
There was one other risk mentioned in the notes that sounded pretty catastrophic. The crash risk.
This is the fatal flaw of standard math when applied to circuits. On a Smith chart, the edge of the circle represents complete reflection. But in impedance terms, an open circuit, like a broken wire, means infinite resistance.
And computers hate infinity.
They panic. They try to divide by zero, and the software throws an exception and crashes. If you're writing code for an autonomous robot that fixes antennas in space, you cannot have the system crash just because it encountered an open circuit.
So the visual nature of the Smith chart, which makes it perfect for us, makes it unstable, slow, and approximate for a robot.
Exactly. We needed a new language, a language that describes the same physical reality, the same hyperbolic space, but uses words the computer understands natively.
Enter rational trigonometry.
Or universal hyperbolic geometry. It's a shift from visual arcs to algebraic polynomials.
Let's break this down. The core promise here is that we can do all this RF engineering without ever using sine, cosine, or pi.
Correct. We replace those standard measurements with rational ones. And when mathematicians say rational, they mean numbers that can be expressed as fractions, integers, no unending decimals.
The notes list two big metrics that replace the old ones, quadrants and spread. Let's start with quadrants.
Quadrants, denoted as a capital Q, replaces distance.
Hmm.
In normal geometry, say the Pythagorean theorem, you have $t plus b2 is c22. To find the actual distance, you have to take the square root.
And square roots are often irrational. The square root of 2 goes on forever.
Right, so rational trigonometry asks a very simple question. Why take the root? Why not just stop at 222? Quadrants is simply distance squared.
That seems almost too simple. Does it actually work for engineering?
It works beautifully. By stopping at the squared value, you avoid the irrational numbers entirely. It allows the computer to work with exact integers, which means zero rounding error. The computer is happier, and the result is more precise.
Okay, so quadrants is distance squared. What is spread?
Spread, denoted as $0, replaces the angle. Instead of degrees or radians, which rely on pi spread, is a rational value between 0 and 1. 0 is parallel, 1 is perpendicular.
So we don't say 90 degrees anymore.
No. A quarter wave transformer, which is a standard component for matching impedance, used to involve calculating phase angles of pi over 2. Now it has a spread of exactly 1.
Just 1.
Just 1, no pi, no degrees, just an integer.
That is cleaner. But what about the complexity of loss? We talked about that spiral, the loxodromic path.
Yeah.
That involves some heavy calculus, right?
In the old world, yes. You calculated decay using e to the power of negative alpha x. That's a complex exponential. In the new rational model, they use a rational decay factor to dollars. It's just a simple ratio.
So we are stripping away the fuzziness of the higher math, the transcendental functions, and turning it into simple arithmetic.
We are teaching the computer to speak its own language.
Okay, I get the definitions.
Yeah.
But I want to see this in action. Let's say I'm an autonomous 5G tower. I detect a signal mismatch. I don't have eyes to look at a Smith chart. How do I actually fix it using this new math?
You solve a puzzle. Specifically, the software uses something called the triple quad formula.
That sounds like a workout routine.
It's a polynomial equation. Q111 plus Q2 plus Q2 plus Q32 equals 2, Q12 plus Q22 plus Q32.
Wait, looking at that is just addition and squaring.
That's the beauty of it. Instead of searching for a visual intersection on a chart like, oh, the circle crosses the line here, the computer solves this quadratic equation to find the exact roots.
And because it's a quadratic equation.
The result is deterministic. That is the magic word in automation. The robot gets the exact same answer every single time with absolute precision. There is no drift.
And what about the crashing problem, the infinity issue with open circuits?
This is solved using projective points. In standard math, impedance is a single complex number, 7 Marty. If 7 infinity, you crash. In rational trigonometry, we describe the state using a coordinate system. EV voltage, current, impedance.
How does adding coordinates help?
Because if you have an open circuit, instead of saying impedance is infinity, you simply write the coordinate as $1.11.
101.
It's a valid coordinate. The system sees it, processes it mathematically, and keeps running. No errors, no crashes.
That seems like a massive reliability upgrade for a system that's supposed to run by itself.
It is, but the biggest impact might actually be on the hardware itself. The sources make a big distinction between CPUs and FPGAs.
Yeah, this part of the reading was really interesting. Why does changing the math change the literal chip we need to build?
Okay, so a CPU, the chip in your laptop or phone, is a generalist. It's like a Swiss Army knife. It has that complex floating point unit we talked about, so it can do everything from word processing to playing video games, which requires all that messy math.
Right.
But rational trigonometry uses only addition, subtraction, and multiplication. You don't need the Swiss Army knife. You can use an FPGA, a field programmable gate array.
Which is what exactly?
Think of it like a chip where you can physically rewire the connections. You can literally hardwire the logic gates onto the chip to do just those specific math operations. You strip out all the bloat of a CPU.
So instead of running software on a chip, the math is baked into the silicon.
Exactly. And because it's just arithmetic, it can perform impedance matching in nanoseconds.
Nanoseconds. Why do we need to be that fast? Is the internet really that impatient?
It's not about patience, it's about beamforming. In modern 5G and future 6G, the antenna doesn't just broadcast in a big circle. It shoots a focused beam of data directly at your phone.
And as you walk down the street, that beam has to physically move to track you.
Constantly, the geometry of the connection is in flux. You need a system that can recalculate the hyperbolic geometry of that wire instantly, millions of times a second, to keep the beam locked.
And the old Smith chart math running on a CPU is too slow and power hungry.
While rational trigonometry on an FPGA is instant.
It's incredible. We went from an engineer with a compass taking 10 minutes to draw arcs on a paper chart to a chip solving polynomials in nanoseconds using pure integers.
That is the journey. And in a way, we're stripping away the human interface. The Smith chart was a translation layer for us. It turned the math into pictures we could understand. But the machines don't need the pictures. They prefer the raw algebra.
There's one final layer to this in the notes that I've found really profound. It mentions field independence.
This is the deep theoretical insight. Standard trigonometry is tied to real numbers. But rational trigonometry works with finite fields.
Which is the math of digital signals, right? Zeros and ones.
Exactly. Cryptography, error correction, digital signal processing, all the stuff that contains your Netflix stream or your text messages, that math happens in finite fields. By switching the geometry of the wire to this rational model, we're finally aligning the math of the physical medium with the math of the digital message.
They are finally speaking the same language.
Yes. We've unified the physics of the wire with the logic of the code.
So what's the takeaway here for the listener? We've covered hyperbolic space, 1930s charts, and robotic polynomials.
I think the big insight is that curved space isn't just something for astronauts or theoretical physicists. It's happening right now, inside your pocket.
In the phone.
In the phone. The signals allowing you to hear this deep dive are traversing a hyperbolic universe inside those tiny wires. For a long time, we humans navigated that universe with drawings and intuition.
But to take the next step, to get to the speed and reliability of the automated future, we had to let go of the drawing.
We had to teach computers to ignore the circles we see and focus on the algebra we can't. We had to embrace the rational.
A little hyperbolic geometry to chew on next time you struggle with your Wi-Fi signal. Thanks for listening to this deep dive.
Keep diving.